Hello, my name is Sienna Rodriguez, and I'm currently completing an independent research project through the Department of Physical Sciences with Dr. Kidan Ha. And basically, our research is focused on identifying a systematic novel psychoactive stimulant classification based on chemical structure and bioactivity. And then we built a representative library to then be used in identifying never before seen substances through the use of molecular fingerprinting. So, what are novel psychoactive substances? NPS are technically considered legal highs because they circumvent the drug abuse legislation, and the Drug Enforcement Administration defines a substance to be illegal based on their specific chemical structure, the drug's potential for abuse, evidence of pharmacological effects, history and current pattern of abuse, and the risk it poses to the public's health. And then it's placed on the controlled substance list for regulation. With that in mind, underground scientists make slight modification to the illegal drug's chemical structure, technically making a legal and unregulated derivative of the illegal drug. The diagram on the left illustrates the overlap we see of the drug structurally and functionally, as well as the wide range of chemical diversity. That's why it's so difficult to create a clean cut way of classifying these NPS. The main concern with NPS is that they have similar structures that produce similar psychoactive effects to traditional illegal drugs such as cocaine, cannabis, and ecstasy. And these compounds are intentionally mislabeled and sold online on the black market under slang terms like bath salts, plant food, and research chemicals. NPS are intended to mimic the hallucinogenic and euphoric highs of illegal substances such as methamphetamine or cocaine, but are actually a lot cheaper and easier to obtain. The main mechanism of NPS specifically for stimulants are monoamine reuptake transporter inhibition and or release facilitation. So the inhibition of dopamine and noradrenaline reuptake by the inhibition of the dopamine activator, active transporter, and norepinephrine transporter, and serotonin transporters cause an increase in the concentration of the neurotransmitters like dopamine, serotonin, and noradrenaline in the synaptic cleft between two neurons, which results in the overstimulation of the sympathetic nervous system and then is actually the cause of those psychostimulatory effects a person exhibits after taking these drugs. The chemical class for these stimulants would include aminoiodines, benzopyrenones, cathinins, phenethylamines, pipazines, and the hallucinogens we study would include phenethylamines, benzodiazepines, and tryptamines, which predominantly interact with serotonin receptors to inhibit serotonin reuptake. These drugs cause a large range of symptoms such as muscular abnormalities, tachycardia, hypertension, palpitation, acute myocardial infarction, cerebral ischemia, psychotic hyperactivity that could potentially result in violence, self mutilation, homicidal combat behavior, coma, and even death. And this is a problem to public health. And approximately 2 new NPS per week were formally notified in 2015, and then over 560 NPS were being monitored. But most recently, as of December 2020, 1,047 substances were reported to the UNODC Early Warning Advisory, and over 500 NPS were reported in the US alone. And so basically, every time we add a new substance to the list, a new one pops right back up. And you can see on the map the range of NPS emerging like around the world, and it's just steadily increasing. So right now there's a technique called Raman spectroscopy, and that uses a laser to shine through the compound, which reflects off of the photons in the molecule, resulting in a spectrum fingerprint in the molecule, resulting in a spectrum fingerprint that's used as an identifier for the drug. So every molecule has its own unique spectrum fingerprint. This handheld device can actually take a sample and then identify whether it's an illicit drug or not by the software that's installed inside of it. And it acts sort of like a library database and is used to reference and compare the spectrum fingerprint of the unknown substance to the spectrum fingerprint of the various known substances in the library database. The device compares the spectrum fingerprint and sort of calculates a probability of how closely related the unknown is to the known substance. The goal of our project is to contribute to the advancement of chemical analysis regarding Raman spectroscopy and designing an accurate, concise, and representative library. The current database library, when analyzed, is not efficient enough because of the alarming increase in new NPS, and it's just simply isn't able to keep up with the amount of new NPS that just keep entering the black market. The other aspect of our research is to understand what chemical features or the pharmacological profile of these new NPS that are responsible for the addictive properties of a drug. The pharmacological profile refers to the specific fingerprint created with experimental assays of NPS against multiple protein targets in the CNS. We're also concerned with the structured molecular descriptor, which refers to the in silico compound computed fingerprint. And it's also important to emphasize that we're using unsupervised and supervised machine learning to conduct a clustering analysis that will allow us to create a representative library to improve the accuracy of chemical identification. So, molecules with structural similarities usually share the same pharmacological activity, and using algorithms, binary fingerprints were created to translate the shape and structural features of a molecule into a language the computer can interpret, and then that would create a unique molecular fingerprint for the various drugs. We were actually able to use machine recognizable methods to quantitatively describe molecular structures by using different molecular fingerprints such as PubChem, Morgan, RDK, and MACCS. We intentionally were looking to see if the molecule contained specific structures of interest, and if it did, it was given a 1, and then if it was absent, it was given a 0. And from this labeling, a substructure fingerprint was created for the molecule. Different molecular fingerprints were used to yield what's called a Tanimoto coefficient to identify how closely related the drugs were. A Tanimoto coefficient ranges between 0 and 1, where a number closer to 1 indicates more similarity. And you can see that in the figure on the right. In the study, we first conducted an unsupervised clustering analysis where we tested 4 different types of molecular fingerprints, which was MACCS, RDK, PubChem, and Morgan, to see which type of fingerprint was most accurate when creating a representative structure for stimulants and hallucinogens. This analysis was also done to see how similar these drugs were from a structural and pharmacological perspective. As you can see, the distribution is different from a structural and pharmacological perspective, so That's why it's kind of important for us to do these analyses to see how they correlate. The similarity of the molecule also depended on the molecular descriptor we decided to use. The scatter plots here show the comparison between the different molecular fingerprints and the data plotted using the drug's structure. As you can see, these plots show a linear distribution. We did see a better correlation compared to the data obtained using the pharmacological data. With the sample, we then use some criteria to evaluate the dissimilarity between the compounds, and then we use the distance matrices to connect the dots and merge it into a larger tree. And then those branches were separated into different clusters using the 4 fingerprint methods to see if the cluster results were correlated with each other. We also established a data mining approach by using a classification model to virtually screen and identify new NPS with high abuse potentials. High throughput bioassay screening data of various targets depicted in the graph were collected from PubChem, which is a public database. So basically their IC50 values were analyzed and then used to label each tested compound as active or inactive inhibitor against the target. Various substructural fingerprints were used as the molecular descriptor. And in order for this model to function, 80% of the data inputted was to train the model to identify whether the substance was active or inactive, and then 20% of the data was used to actually test the performance of the model. The second test set was generated using the NPS dataset. So the test set used the RDK fingerprint, which had an average MCC score above 0.75 for all targets. And that actually indicated an excellent performance of the trained classification models using support vector machine. And due to the differences in compound distribution and limitation from the PubChem screening data set, the performance was in general worse when evaluated with the NPS set, but the RDK fingerprint still produced the best performance for all the targets except CERT and D2. So thank you for listening to my presentation, and I hope you have a great rest of your day.